Okay, let's have a brief conversation about what I'm going to call the current equation. Now, if you think about the different equations that exist for current, then I'm going to write a few of them down. Q equals IT. Now, this equation is the definition of current. If I rearrange, I can get I is equal to Q over T. And that would be equal to, if I was to say in words, the flash way, if you like, of saying charge divided by time is charge flowing per unit time, or the charge flowing in 1 second. Okay, now there are other equations that have got current in them, like for example, F equals BIL, but that equation is nothing to do with DC electricity. That's to do with magnetism. I'm just going to put a line through that. That's magnetism. But I actually, at this moment, want to talk about electricity and the flow of current. Problem with Q equals IT is it's purely the definition of current as an equation. There's another one, which is sometimes called Ohm's law, V equals IR. And what this tells us is what determines the value of a current. If I rearrange that formula, for example, I get I is equal to V over R. So it will tell me that the current flowing will depend on two things. It'll depend on the voltage, and that's kind of like saying the electrons are flowing through the material at a certain rate, because of course as the electrons move they carry their charge with them, and they're flowing through the material at a certain rate which is determined by the force from the power supply. And if I increase the voltage, I'm increasing the force on the electrons, and it kind of makes them move faster. And the resistance, that's the opposition to the flow of the electrons. And that's basically the atoms getting in the way and scattering them. But the problem is that this equation does not really break down in fine detail the factors that determine the value of a current. And so there is another equation, and its name is a little bit like saying the equation. If you just bear with me a second while I just expand on that. When we say Q equals IT, very often this is memorized as quit, just like electrical power, P equals IV, is often said as PIV. Well, this one is said as its kind of letters as well. And the equation is, and this is the one that I'm referring to as the current equation, I equals NAVE. It's called nave, which has got nothing to do with churches, which also have a nave. Okay, so now this equation is really useful for us because it tells us the value of a current with respect to the properties of the electrons and also the properties of the material that it's going through. So this is a really useful equation because it allows us to work out what's going on when we have a change of current. Now, the equation comes from the idea that if you imagine that you had a circuit with a voltage, I'll call it V0, and I'm going to kind of make it like a big capital V there. And imagine that I've got a circuit here, very simple circuit, just a resistor. And actually, I'm not interested in electrons sort of going through the resistor or going through. I'm just interested in electrons moving, that's all. I'm not interested in discussing in detail the scattering process. So just imagine that we could draw a zoomed in version. Now, the way that I've got the circuit here, current is coming out of the positive terminal, so it's going in that direction, which means electrons are going around the circuit in that direction, clockwise. So I've got some electrons here, and of course there'll be lots and lots and lots of them, and they're all moving in this direction. Now, I know that they're scattering. They're accelerating and bouncing off and decelerating and accelerating and decelerating, but they'll have an average speed, which is also called the drift speed, or sometimes called the drift velocity. If you imagine the definition of current, then we can say that the current is equal to the charge flowing per unit time. What you have to do is imagine that these electrons are moving through the circuit. And you're basically saying, imagine I had a stop clock or a timer, and I started the timer, and I could literally count the electrons going across that blue dotted line. And if I knew that for a certain period of time, so if I could do it for, let's say, 1 second, if I knew that there were 50 million electrons that went past my dotted line in 1 second, then that would be 50 million electrons per second. And the total charge would be 50 million electrons times the charge of an electron. So if I get back to this formula here, I can say that current is the charge flowing over time, and the charge flowing is the number of electrons multiplied by the charge of an electron, which very often in physics we use the letter little e for the charge of an electron, divided by time. Now, the number of electrons we have in physics, when we talk about materials, little n, and little n is the so-called number density of electrons. The number of electrons per unit volume. Outrageously, that would be the number of conduction electrons, free electrons that can move in 1 cubic meter, because in SI units, per unit volume would be 1 cubic meter. That's a big lump of stuff. And that would be N over volume. I've written the word vol for volume because I do not want to get confused with the V that I'm using for voltage or the V that I'm using for drift speed. So if I look at this equation, it means that I can write that N is equal to little n times the volume, just by rearrangement. Therefore, this can go into this equation here. So the current is equal to big N, which is N times volume times E over T. And then finally, the volume of the wire is equal to the length of the wire multiplied by its cross-sectional area. So I can write this as little n times the volume, which is A times L times E over T. And finally, the length over time is the drift speed. So I end up with I equals N A V E, Nave. The importance of this equation is it tells us what is happening inside the material when the current changes. So if, for example, someone were to say, okay, the current has increased. Why? Now, the simple answer might be, from just looking at V equals IR, the current has increased because either the voltage has increased, which is the driving force, or you can consider it to be the driving force. Voltage isn't a force, of course. And or the resistance has decreased. But it's not fantastically helpful because it doesn't explain what has actually happened. This equation, the so-called current equation, does. Basically, A is the cross-sectional area of the wire. Now, no matter what I do to a wire, that's basically considered to be the same. And E is the charge of an electron. And whatever we do, the charge of an electron is the charge of an electron. So those two things really are constants. This is the drift speed. If current has increased, it normally means V has increased. Because if V has increased, the drift speed, then it means the electrons are moving faster, which means the charge flowing per second has increased. That's why the current increases. The number density is a constant for metals. So if we're talking about copper wire in a circuit and someone was to say the current has just increased, why? The answer could be as simple as, well, I've increased the voltage, or I've decreased the resistance, or somehow a bit of both. But the bottom line is, it's because the drift speed has increased. If the drift speed has increased, that could be because the voltage is increased because that will provide a greater driving force and that will make them go on average faster. Or if the resistance somehow is decreased, again, that means the electrons can flow faster. Now, for semiconductors, N can change. In a semiconductor, energy can be used to free electrons so they can conduct. And if you remember, N was the number density of electrons, but these were the conduction electrons. These are the free electrons. They're not all of the electrons. They're the ones that are available that can carry a current. And in a semiconductor, energy can be used to free electrons so that they can conduct. If it uses thermal energy, that creates what we call a thermistor. If it uses electromagnetic, in other words, light, that's what we call a light-dependent resistor. So, to summarize this bit then, I is equal to NAVE, and for metals, only V can vary, whereas for a semiconductor, that can vary and that can vary. So semiconductors are more complex. Note, if we have a thermistor, the resistance of a thermistor as a function of temperature falls. And for a light-dependent resistor, again, the resistance as a function of light intensity falls.